Okay, so today we'll talk about angular momentum. Okay. In physics, like I've said before, we look for, a system will be evolving. So you saw a pool table in the rack, you broke a rack. That was a complicated motion of many particles. Okay. And you wanted to know quantities that were conserved. Okay. So we'll learn today about a new quantity, angular momentum, and it is conserved, okay, in many situations. And we'll see when it is conserved. Okay. So this is the parallel of, we'd introduced linear momentum, which was mass times velocity. And Newton's second law, what is Newton's second law? And so force equal mass times acceleration, that was a special case. Here was the more general case. Okay. Force was equal to time rate of change of angular momentum. Okay. When did this reduce to mass times acceleration? Yes. Yeah, when dm by dt was 0. Okay. So you couldn't apply this to the case of a rocket. Okay. This is what you would use. Okay, so similarly, we'll introduce today something called angular momentum. It's denoted by L. It's a vector quantity, so hence the arrow on top. Okay. And Newton's second law will be torque will equal to dl by dt. We've talked about torques of forces last class, but this is Newton's second law for rotational motion. And that's what we're introducing. Okay. And what you'll see in the chapter today, so you encounter a lot of situations in the natural world where the torque acting on a system is 0. So that means dl by dt is 0. So the angular momentum is conserved for that quantity. Okay. So for instance, I guess I'll give you an example. So here's a pretty spectacular example. All right, so here's a model of the solar system. Do you guys know how far apart this thing is? What is the distance between the Earth and the Sun? 92 million miles, 100 million miles, okay? And so if this were to scale, the solar system is as large as this room. Okay? And the solar system was formed on this scale, the solar system was formed from a cloud from Dunn Avenue to White to Clyde Morris to ISB. Okay? So that's how large a cloud it was formed from. Okay. And that cloud was slowly turning. Okay. You guys seen an ice skater, right? An ice skater spin, and when he or she brings their arms in, what happens? They spin faster. Okay. So this cloud, as it collapsed, it spun faster. A spinning object has angular momentum. This all started about 5 billion years ago. The angular momentum of that cloud has been the same for 5 billion years. Okay? Now the angular momentum is in the spinning sun. The sun is spinning about once a month, and the planet's going around. It's mostly in the spinning sun. Okay, the sun has 98% of the solar system mass. Okay, so here's a spectacular phenomenon. It's a system that has been evolving for 5 billion years. And that's a pretty spectacular statement to make. Its angular momentum has been constant. Okay. All right. We can't say its energy has been constant because mass has been if you just look at the solar system, we've been converting mass to electromagnetic radiation, which is being radiated away. So, All right, so we'll talk about angular momentum. Okay, so we'll introduce to you the Newton's second law for rotational motion. So first we'll start off by talking about a rolling motion. Okay? And the reason we're talking about that is because in the first 9 chapters you talked about translational motion. What was translational motion? The center of mass of the object was moving. Every particle of the object was moving with the same velocity. You treated it as a point particle. And then in the last chapter we talked about rotational motion. We talked about pure rotation. Now, if you combine the two, you get rolling motion. Okay, so that's what we're going to talk about. And then we'll get to the main chapter. Okay. All right, what this picture shows you is the following. And I know I'm recording this, but so I got to come back here. Okay, so what happens is if a wheel is rolling without slipping, okay, and it's got to roll, so its center of mass has got to move at constant velocity, you put a light here on the rim. That light will trace this curve. And that's called a cycloid. Okay? And there is the center of mass of the wheel going in a straight line. Okay? All right, so here is pure translation. If you take an object and it executes pure translational motion, every point is going with the same velocity, it has the same displacement and all. And you can treat this as a point object, and that's what we were doing the first 9 chapters. Then you looked at a rigid object rotating. Okay, so here was the axis of rotation. Okay. So the axis of rotation is coming out of the plane of the paper. And this point is going in this direction. Opposite points, points at equidistance from the axis, have opposite velocities. Okay? And you can see that. So I'll spin this wheel. This is a rigid object rotating. This point is going in this direction. This point is going in this opposite direction. Okay? And remember, the linear speed of this depends on the angular velocity of the object times how far you are from the axis of rotation. All right. So now let's do the following. We know how to add vectors. Let's combine these two. We'll just add the corresponding vectors. Let's add this to that. You get this vector twice as long. Let's add this to that. You get the center of mass velocity. You add this to this, you get 0 velocity. So when a wheel is rolling, the point of contact is momentarily at rest. Okay. Now, if this wheel is an ideal rigid wheel, okay, and this was a rigid structure, you get it rolling, there would be no friction and it would roll forever. Okay. But what happens is the wheel deforms and the surface deforms, and so there's a small rolling friction that's in the opposite direction. Okay. And so it'll slow down. Rolling friction is smaller if the wheel is fully inflated. Okay, so your gas mileage gets better. Okay. Of course, if you overinflate, then you have a problem of maybe the tire blowing up. So you got to balance better mileage and safety. Okay. And you, as a motorbike rider, know that very well. All right. So rolling is a combination of rotation and translation. Okay. All right, so now let's look at it in detail. So this wheel is rolling, and as it rolls, when it rotates through an angle theta, you see as this wheel rotates, this point will come to the ground. So the wheel has traveled a distance s. And S is related to the radius of the wheel and the angle through which it's rotated. So S is, remember, if you remember the original definition of theta, theta is S over R. And in this formula, theta is in what units? Radians, okay? So the distance the wheel has traveled is R times the angle through which it's rotated, okay? And now, you can use your calculus machinery, okay? You take the time derivative of that, that'll give you the velocity. That'll give you actually the center of mass velocity. The radius of the wheel is not changing, okay, hopefully for you guys. Okay. And so dr theta, so this will be, r will come out, and d theta by dt is the angular velocity. Okay, so the center of mass velocity of the wheel is equal to the radius of the wheel times the angular velocity of the wheel. So you've seen cars with bigger wheels. They'll replace the normal size wheel with a bigger wheel. Why do they do that? Well, your motor engine will give you a final angular velocity, and if you have a bigger wheel, you can get a bigger linear velocity. So you can go faster with a bigger wheel. Again, take the derivative of that. The center of mass acceleration, again, r is constant, is r times alpha. So the center of mass acceleration is the wheel size times the angular acceleration. Okay? And to get angular acceleration, you of course need torque. Okay? And so if you look up here, and we'll come to this, so this is the moment of inertia. Greater the torque, greater your angular acceleration, greater your linear acceleration. So you guys can look up all your cars, specifications of cars. They'll tell you what kind of torques are provided at what RPM. Okay. So that tells you what kind of acceleration you can get with your cars. Okay. Now, any object that is moving has kinetic energy. Okay, so as the wheel is rolling, okay, so you can think of it as rotating about this point. This point is at rest. Okay, so the kinetic energy is 1/2 I, the moment of inertia about this point. That's what that says, moment of inertia about point P, times the angular velocity squared. This was the kinetic energy formula that you saw last time. All right, so this is the moment of inertia about the wheel at that point. Now you saw the parallel axis theorem. Okay. The moment of inertia about any point is the moment of inertia about the center of mass plus mass times that distance squared. Okay. So what we're saying is the moment of inertia of the wheel about that point is equal to the moment of inertia of the wheel about that point plus the mass of the wheel times r squared. Okay. And we're going to substitute that here. And so this term is the kinetic energy of pure rotation. Pure rotation. Okay. So in formula we are showing you, so this is the kinetic energy of pure rotation, and this is the kinetic energy of pure translation. So the kinetic energy of the rolling motion is the kinetic energy of pure rotation plus the kinetic energy of pure translation. And the V center of mass was r times omega. So V center mass square is r squared omega squared. All right, so this formula just shows you that, again, we stated it, that rolling motion is pure rotation plus pure translation. All right, so when you accelerate in your car, here's what is happening, or on your bike or whatever. Okay. What your engine tries to do is it gives you angular acceleration. So this wheel is trying to rotate faster and faster. And this point of contact is trying to slip. And if it slips, then you're not going anywhere. So the motion of your car is dependent on the fact that this is not slipping. And what is preventing it from slipping? It's a static friction force that's preventing it from slipping. So the static friction force that the road applies, that is what is accelerating your car. Okay. You guys have seen drag racing? Okay. So in the drag racing, what is it that they do first? I'm sorry? They do a burnout. Why do they do a burnout? Yes, so what they're doing is, so the maximum static friction force is mu s times the normal force, which is equal to the weight of the car. You're not changing the weight of the car. With the burnout, you're increasing this number. Okay, you're increasing mu s. You can increase the maximum static friction force, and you can have the maximum acceleration. Okay, so that's what you're doing. Yep. All right. I'm just so now let's say you have a wheel that's rolling down a ramp. Okay. So there's the weight of the wheel. There's the component of the weight. So this is mg. This is mg sine theta. This is mg cosine theta, and that's equal to the normal force. Okay. And this is the static friction force. Okay. So as the wheel rolls down, again. As the wheel is rolling down, so it is accelerating down, and the center of mass acceleration is g sine theta. So, yeah, so let me draw another diagram here. So if you took an ice cube and it was on a frictionless surface, and the acceleration of this ice cube is g sine theta. Okay, you saw that in one of the previous chapters. Okay, so it's g sine theta. So if an object is rolling down without slipping, it turns out that the center of mass acceleration is smaller than this. Okay, so a wheel rolling down is accelerating at a rate that is smaller than a object sliding down. It's g sine theta divided by this guy. Okay, and you see this number is greater than 1. Okay, so the acceleration of the center of mass of the wheel is smaller. It is accelerating, it's translating, and it's also rotating. Okay, so the acceleration is smaller. So what is happening is, when this guy was sliding down, potential energy was being converted to kinetic energy. Pure translational kinetic energy. In this case, potential energy is being converted to translational kinetic energy and rotational energy. Okay. So that's what this is showing you. Okay, what this equation is mg sine theta minus the friction force. This is the total force acting on it minus the friction force. That's equal to mass times the acceleration, and we'll calculate the torque about this point. So these two forces do not have any torques. This force will have a torque about this point, and this force won't have a torque. So Fs times r, that is the torque acting on this object, is the I center of mass, the moment of inertia. Torque is I times alpha. Okay, and then alpha is related to that. Alpha, A center of mass, is alpha times r. Okay, and so between these three relationships, you can derive that. Uh-huh.
Is that a 1?
With this one is 1.
Okay, yes.
That is 1. Yep. And this is the moment of inertia by the center of mass. All right, so again, I don't want you guys to get lost in this. What I want you to remember is, if an ice cube is sliding down in a frictionless manner, the acceleration is g sine theta. And if a wheel is rolling down, the acceleration of the center of mass is smaller, and it's smaller by that amount. And you can see that greater the moment of inertia, smaller the center of mass acceleration. Okay. And how do you get greater moment of inertia? The further the mass is distributed from the axis of rotation, the greater the moment of inertia. Okay. So for instance, here are three objects of equal mass and equal radius. This guy has a mass distributed further from the axis than this guy. So this guy has a greater moment of inertia. He will accelerate down slower than this guy. Okay, this guy will reach first compared to that guy. Okay, and then this guy, so this guy has the lowest. This guy will reach first, and between these two guys, you have to decide which one has the greater moment of inertia. It'll depend on this guy. If this guy is just a thin wheel, he'll have the greatest moment of inertia, and he will reach last. Okay, so it all depends on the inner radius. The moment of inertia of a sphere, of a bowling ball, you can look up those tables. The moment of inertia is, I believe, 2/5 mr squared. Okay, the moment of inertia of this guy is 1/2 m r1 plus r1 squared plus r2 squared. R1 and R2 are the inner and outer radii. Okay, so depending on which one is larger, tells you which one will reach the ground first. Okay, so what this formula gives you is the center of mass velocity after the objects have fallen through a height h. Okay. All right. All right, now we'll prepare you for Newton's second law. Yeah. What is Newton's second law for rotational motion? The torque is equal to time rate of change of angular momentum. Okay. So that's what we're going to derive. Okay. So this is the parallel of force equals to dP by dt. Okay. Force got replaced by torque. Linear momentum got replaced by angular momentum. Okay. All right, so here's how you define torque. Okay. So here's an object, here's a force acting on this object at this point, and the torque of this point is R cross F. What is R? R is the reference point. Okay, so there's the R vector. R cross F is the torque. So how do you choose the reference point? You can choose the reference point to be anything. Okay, so you can calculate the torque about anything. The torque of this force about this point is 0. If you calculate the torque about any point along the line of action of the force, it's going to be 0. Okay, so you can calculate the torque about any point. Okay, so you got to keep that in mind. The torque depends on what point you're calculating the torque about. Okay, for a given force. So in this equation, well, you learn that the torque depends on the point about which you're calculating the torque. The angular momentum will depend on the point about which you're calculating the angular momentum. You'll see that in a second. So what do you think is natural about this equation? What do you expect of that equation? You need to be calculating the torque and the angular momentum about the same point. Okay? So, I mean, that's obvious, but no. Okay, so that's what we'll do. Okay, so here's angular momentum. Here's angular momentum is denoted by L. Okay, and so let's look at this disk. Here's this point, this little bit of the going at that velocity. Okay, and the angular momentum of this guy about that point is defined very similar to torque. It's R. R is the vector from the point about which you're calculating the angular momentum. What point do you calculate the angular momentum about? You can calculate it about any point. Okay, so about this point, angular momentum of this guy is R cross P. P is his linear momentum. Okay. So the angular momentum is that guy, and R cross P, here's R cross P is in that direction, R cross P is a vector in that direction. So the angular momentum of this piece is in this direction, and you can calculate the angular momentum of all the pieces, and you'll see that they're all pointing in that direction. And the angular momentum of the total object is just the sum of all those angular momentum, of all those little pieces. Yeah. All right, so now we'll sort of derive the Newton's second law, okay, for the very simplest case. Okay? And then we'll say, well, it's good in general. Okay, so we'll take a point object, apply a force on it. Okay, so it's just it's a baseball or whatever, and you're applying a force on it. Okay, and we'll choose this point to calculate angular momentum and torque about. Okay, that can be any point. You can choose any point. Okay, so we apply a force. So, and the torque of this force about that point is R cross F. R cross F. So if you bring R there, R cross F, the torque is pointing in that direction. Okay. R cross F. Remember, you use your right hand rule. When your fingers turn from the first vector to the second vector, your thumb points in the direction of the torque. Okay? Your fingers turn from here to there, your thumb points in that direction. All right, so R cross F is the torque, that's the torque. What does the force do? It accelerates the particle. It's R cross D, it changes its linear momentum. That's what this guy does. Now, so in proving this, here's the little trick. Do you guys remember what is A cross A? A vector cross with itself? Anybody remember that? I'm sorry? No, that's A dot A. This is 0. A vector crossed with itself. Okay, so A, B, phi. A cross B, the magnitude of this vector is magnitude of A, B times sine phi. And if you cross A with itself, phi would be 0 and sine 0 is 0. So a vector crossed with itself, and when else is sine, for what other angle is sine 0? 180 degrees. So a vector parallel to itself and anti-parallel vectors, parallel vectors and anti-parallel vectors give you cross product of 0. Okay, so we're going to use that. So R cross F is R cross dP by dt. F is that. Okay. Now, see, we can throw in dr by dt. Dr by dt is velocity. Velocity is momentum divided by mass. Okay. And momentum cross momentum is 0. So we can throw that in here for free. Because this guy is 0. And you can always add 0 to anything, and they won't be happy about it, but they can't complain about it either, right? So this is 0. Well, why did we add that? Because now we can use that chain rule. This plus this is derivative of this guy. And why did we do that? Well, this guy is angular momentum. Okay. So torque is time rate of change of angular momentum. So there is your Newton's second law for rotational motion. Okay. So in this derivation, you calculated the torque about that point, and you calculated the angular momentum also about that point. And it makes sense. You have to calculate both the quantities about the same point. Okay. And that equation is valid as long as you calculate them about the same point. What point can you calculate? Any point you want. Okay. All right, so that was shown for a single particle. It turns out that it's valid for a system of particles as well. Okay, so if you have a bunch of particles, you know how to add vectors. So you just add up the angular momenta of various parts of the system. Okay, that is the torque acting about each portion. The total torque is just sum of all the torques. Okay, so the net torque acting on a system is equal to rate of change of angular momentum of the system. Okay. So this equation applies to a single object, and it applies to a system of objects. Okay, okay, now we'll prepare to see some of the spectacular applications of this. Okay, so this is the net torque. So on any system, there could be internal forces. Okay, so let's say this system has a couple of internal forces. You calculate the torques about this internal forces, and the torque of internal forces always add up to zero, because these internal forces are always equal and opposite, and the torque due to those forces will always add up to zero. So the net torque acting on a system is just the torque acting due to external forces. Okay. So the net torque acting on a system is external torque. So we can now write this equation explicitly as the torque due to external forces. External forces are what change the angular momentum of the system. Internal forces will not change the angular momentum of the system. Yep. Mm-hmm.
I think I'm a little confused on just the term torque. Why exactly are we interested in it? Like, what is it telling us?
Well, forces give you linear acceleration, and if an object has angular acceleration, then that means there's a torque on it. Okay, so let me give you a simple example. All right. So this force will make it accelerate. Now, acceleration is zero. Okay, those two forces add up to zero. These two forces add up to zero as well. But now the object is spinning. So torque is not zero. So there are situations when an object will spin, and then those forces, the torques of those forces are non-zero.
So is it sort of measured how much it's spinning?
Yeah, torque is a measure of the angular acceleration. Yeah. The angular acceleration will depend on how large a torque is acting on the system. So you talk about torques when objects are spinning. Yep.
So, torque seems to be in the direction of the axis of rotation.
Yeah. Mm-hmm.
How does that really work, though? Because, like, I'm imagining if something's spinning, you have to apply the force in a direction one way.
Okay, so here I'm applying a force like that. So there was R cross F. R cross F, there's the torque in that direction. And that's the direction of the angular acceleration. Yeah. Cross products, so the vector is in a plane perpendicular to the R vector and the force vector. The torque is in that direction. Okay. All right, so this equation is so the external torque. So what we have reduced is what we have gained by saying that is, okay, so we introduced that the net torque was equal to dL by dt. And what we were able to say is that this net torque is just the external torque acting on a system. Okay? And now I'll show you some spectacular examples soon. When the external torque acting on a system is zero, then dL by dt is zero. That means L is constant. Okay, so remember we started this chapter by saying the following. I told you that here is the cloud from which the solar system formed. This cloud was spinning slowly 5 billion years ago. It had angular momentum, and that angular momentum has been constant for 5 billion years. So what was I saying? I was saying there's no external torque on the cloud. That's what I was saying. Okay? See, I can make this spin faster if I apply an external torque. And now if I don't apply any more external torque, this should be spinning 5 billion years from now. Right? So because there is friction, that stops. Just like, when I threw that baseball in space at 90 miles an hour, that thing went on forever. When does it go forever? If there's no force acting on it, slowing it down or accelerating it. Just like that, okay? So if there's no torque acting on the system, external torque acting on the system, L will be constant. Okay, so the net torque is, okay. Both torque and angular momentum depend on the choice of the origin for the coordinate system. We said that. The relationship between torque and angular momentum is independent of the choice of that point if the center of mass of the system is not accelerating. Okay, this is just technical details. For axis passing through the center of mass, this is always valid for axis passing through the center of mass. Okay. For a particle moving in a circular orbit, angular momentum is r cross p. P is m times v. And since r and p for circular orbit, these are perpendicular to each other, sine phi is 1. It turns out that the magnitude of angular momentum is mvr. So this is a good one to remember. Okay? For a particle moving in a circular orbit, the angular momentum is just mv times r. So for a rigid object, the angular momentum of this piece is mvr. That's the angular momentum of this piece. Vi is ri omega. So if you substitute that, you get mri square omega. And then if you want to get the angular momentum of the whole thing, just add them all up. So that should have mi square omega. But this guy is just the moment of inertia of the object. So the angular momentum of this rigid object is I, the moment of inertia of that object, times the angular speed. Okay, so here's a parallel of linear momentum is mass times velocity. Okay, angular momentum is I times omega. So this is true when the moment of inertia is not changing and it's for a rigid object. Okay. So the angular momentum is I times omega. So here is Newton's second law. And this reduces to F equal to ma when dm by dt is 0. Okay. Similarly, torque is dl by dt. And this reduces to torque is I times alpha when di by dt is 0. When the moment of inertia of an object is not changing. So for instance, when a skater pulls her arms in and or out, the moment of inertia is changing, and then this equation is not valid. Okay, so this is valid only when moment of inertia is constant. Okay, now we'll talk about some fun stuff. All right, so we'll first talk about precession, okay? So you guys have all seen this, and we'll just give some technical terms to these things. And I guess I can't record all of this, but all right. So you see, here's this wheel. Here's the center of gravity of the wheel. The force is acting like that. If you calculate the torque by that point, there's R cross, R cross, R cross, oops, R cross. So this times this gives a torque in this direction. The torque direction is that way. Okay? You guys understand? R is in the air, there's the force. So R cross this force gives you a torque. Okay. If I let go, what that torque does is it gives a spin this way. This just fell. It spun around that axis, and there was the L. So L increased in that direction. Okay, again, this is very confusing. So I let go, and it just fell. Now watch this magic. So it's the same torque. Now look at the effect. I'll have to do it on the floor. So the same torque is making it precess. So you gave it an angular momentum, and the angular momentum is changing. So there's R, there's the R cross mg is a torque coming out of the plane of the paper. And if you gave the top a spin, that's the direction in which the angular momentum will change. So it had an angular momentum like that, and the angular momentum will change. And as it keeps turning, it will keep the change in angular momentum will be on the surface of this cone. And the object will precess. Okay? And it turns out that the faster this is rotating, the slower the object will precess. Okay? So the effect of the torque on a spinning top is to make it precess. Okay. You can do this using a gyro as well. And all right, here I'll show this to you. So. If this has no angular momentum, that weight will just make it topple. See that same torque is making this. So angular momentum will do it. You really have to know the technical details to understand it. You can't understand it intuitively. Okay. So the faster it's spinning anyway, so the angular momentum, change in angular momentum will be in that direction, and the wheel will spin like that. Okay. What this tells you is the angular speed of precession, or speed at which it's going around, and this is small omega is the angular speed of the wheel rotating. So you see, the faster it's spinning, the slower it'll precess. Okay. That's what it's saying. And this is valid for, this spinning much faster than that. All right, so now let's talk about conservation of angular momentum. So we saw Newton's second law was external torque was equal to time rate of change of angular momentum. Okay. So if external torque is 0, then the angular momentum should be constant. dl by dt is 0, L should be constant. And you could do this experiment. and apparently this thing works for about 3 feet. So you can grab, if you have a cat, grab hold of its feet, yeah, and drop it. So the cat is upside down. Okay. When you drop it, its angular momentum is 0. The force of gravity goes through its center of mass. The torque, that's the only external force acting on it. The external torque is 0. So what we're saying is, as the cat drops, its angular momentum is constant. And apparently, so you can watch this YouTube video, it'll always land on its feet. So what's going on? So what the cat does is, it rotates its lower body or tail in one direction and its upper body rotates in the other direction. So its angular momentum is 0 all the way through. Okay? And then the front, when it's in the right direction, it lands on its feet. So you guys have all watched football, and why do you throw the football with a spiral, with a spin? Why do you throw it with a spin? Okay, so here's why you throw it with a spin. Okay, so on a windy day, if the football wobbled as it was flying, the drag force would change. If it wobbled, the drag forces is fluctuating all the time. Okay, and this supercomputer of yours, okay, so you throw the ball and somebody is running up to the ball and catching it. The supercomputer is doing the calculation. So if the orientation of the ball remains the same, then this computer is able to calculate the drag. This is minimal drag. So what this is showing you the relative velocity of the wind. So as you throw the ball with a spin, if it's spinning like this, there's the angular momentum. There's the angular momentum. That drag force is, the external torque is 0, so this angular momentum remains constant. So you see no external torque acts on it. The angular momentum of the football remains constant. Okay, when it's maintaining its orientation constant, you can calculate the drag force. What this is showing you is the relative wind velocity. Okay, so as the ball is moving in this direction, there's the air moving. Okay? And this, your supercomputer is able to calculate. Soon as the ball wobbles, that becomes very hard. Okay? So go on a windy day and play football on the beach. You throw it with a wobble, people will be dropping their catches all left and right. And throw it with a nice tight spiral and they'll be catching it. Yeah. All right, so here's the skater. In this configuration, the moment of inertia is high. Moment of inertia is high, and in this case, moment of inertia is low. Okay, so as this system evolves, there's no external torque acting on this system, and the angular momentum remains constant. So initial angular momentum is equal to final angular momentum. Since this is small, this is large. In fact, this happens in stellar objects quite spectacularly. So for instance, the sun, the radius of the sun, you can look it up as, I think it's about 700,000 kilometers or something like that. You can look it up. Okay? And the sun will eventually become a white dwarf. And its radius will decrease by a factor of 1,000, something like that. Okay, so the moment of inertia, which is related to mr squared, 2/5 mr squared, will decrease by a factor of 1,000,000. So the sun will start spinning 1,000,000 times faster. Yeah. Of course, you have to wait another 5 billion years for that, but come back in a little bit. You know? All right, so here is this fellow on a merry-go-round. As he walks to the center, the moment of inertia of the system is decreasing and it'll spin faster. Okay. So here's a very good demonstration, and again, it's like I said, angular momentum stuff are hard to understand. There's no way to guess and predict what will happen. So. So let's see what's going on. All right, so she's got this wheel spinning like that. There's the angular momentum of this system. There's no external torque acting on the system. So whatever the system does, what should be true? The angular momentum of the system should be constant. Okay, so you saw me flip the wheel. Okay, so I'm going to draw. So here's the person, here's the wheel. Okay, and the angular momentum of this wheel was 20 units. I'll just make up some number. Okay, then what did I do? I flipped the wheel. So it was rotating in this direction. I made it rotate in this direction. Now the wheel has an angular momentum of 20 units in this direction. But I said that the angular momentum of that system had to remain constant. So what had to happen? You saw me spinning in this direction, and I have an angular momentum of 40 units in that direction. Yeah. So that's what was happening. Yes, so here's another instant of constant angular momentum. So when this diver jumps off, okay, so her center of mass is in front of the edge of the, in front of her feet. So she gives herself an angular momentum. Okay, and in some competitions, you have to spin two times before you enter water, or 3 times before you enter water. Okay, so what is it that you do? Well, if you have to spin 3 times, what you do is you scrunch yourself, your moment of inertia is decreased, and you're spinning fast, and so you spin how many ever times you have to spin, and then straighten out. Yeah. So that's what the training is. How long are you crunched up, and maintaining that, and you're spinning and counting and making sure that you go straight in the water and not hurt yourself. Yeah. All right, so this kind of stuff is useful. Okay, so here's a satellite up in space, and so what you're doing is you're bouncing signals off the satellite like that. So here's your broadcasting station, and you're charging all these people money. And let's say for some reason your satellite, something hit it and it turned that way. Now all these guys are not paying their bills, right? So you got to turn it back. So all these satellites have gyros. If you want to turn the satellite, if you have a gyro that spins that way, then the satellite will turn. So it'll have 3 gyros to turn in independent direction. A gyro that spins that way, a gyro that spins that way will spin it like that. Gyro. Okay, it turns out that what?
I was literally just thinking about this. It's like, does this have to do with that spin up, spin down?
Yeah,
We talk about for electrons.
it's a fundamental quantity. Okay. So at the microscopic level, all particles have a angular momentum. Okay. So there's roughly, I mean, again, this is a ballpark number. There's roughly 10 to the power of 80 electrons in the universe. Okay, so if you want to talk about angular momenta of microscopic particles, you know, when you want to get the distance from here to Jacksonville, you have to use appropriate units like kilometers. If you want to measure the width of this room, then you use a meter and so on. You want to measure the angular momentum of these guys, this is the unit you want. H bar. This is the Planck's constant divided by 2 pi. Okay, so that's the unit you measure in. And it turns out that every electron is spinning, and here's the amazing part, and it's spinning at the exact same rate. Okay, so the angular momentum of an electron is 1/2 h bar. The angular momentum of a proton is 1/2 h bar. The angular momentum of a neutron is 1/2 h bar. Okay. It turns out that the angular momentum of all these guys is 1/2 h bar. Okay. If your angular momentum is a half integer times h bar, then you're called a fermion. If your angular momentum is an integer times h bar, then you're called a boson. And these guys behave very differently. Okay. So you can only put one fermion in a quantum state. You can put as many bosons as you want in a quantum state. Okay. So thanks to this rule, you have a structure for the atom. So here's the nucleus, and here's one quantum state. How many electrons are in the inner orbital? How many electrons are there in this orbital? There are 2. Well, I just said that you can only put one electron, one fermion in a quantum state. Well, one of this is spin up, the other is spin down. So there's quantum states are different. Okay. The next level has 3p level sublevels, and 3p sublevels and an s level. So it turns out that you can put 8 electrons here. So there are sublevels that I've not drawn, but that's the shell. Okay, their energies are all the same and so on. Okay, so that's what gives you the structure of the atom. Okay, so if they were not fermions, all the electrons, you have 100 electrons, you could, if they were bosons, you could put them all in the lowest energy level, and then you would have no chemistry at all, and you couldn't have all the variety that you have in the universe. Okay. So fermions only, so half integers are called fermions, and integer times h bar are called bosons, and all these are force carriers. Okay, force carriers are bosons. Photons mediate electromagnetic force. The gluon mediates the strong force. The Z and W boson mediate the weak force. Okay. So these are the 6 kinds of quarks, top quarks. Only these guys are stable. Okay. So if you see a stable particle in the universe, what are the stable particles that you see in the universe? Protons, neutrons, and electrons. Okay. So protons and neutrons are made out of these guys. Electrons, there's the electron. Electron is a fundamental particle. Okay. You make particles out of any of these guys, they will decay very fast. Okay. So so here I gave you the structure of the I gave you the structure of the atom. I said there was the nucleus and there is the lowest orbital. Well, why isn't the electron orbiting like that, or there? What about all those orbitals? Why aren't they allowed? So it turns out that the orbital angular momentum, that is also quantized. It can go only in a certain circle where the orbital angular momentum is n times h bar. So that is quantized as well, okay? So you can't be in an orbit where the orbital angular momentum is 3.5 h bar, okay, or 3.4 h bar. So that's what Mr. Bohr told us. The orbital angular momentum, MVR, remember, angular momentum was MVR. And again, these are, okay, so it has to be h bar. That's how you know what the orbitals are. So you've heard of these quantum numbers. So this corresponds to n equal to 1, this is n equal to 2, n equal to 3, and so on. Okay. So this gives you, we talked about the solar system. The angular momentum of this system has been constant for 5 billion years. All right, so here's a very spectacular example of precession. Okay. All right, so we'll use this diagram. Okay, so going back, you saw that if you have a spinning top, if the top was spinning, it has angular momentum. And if a torque acts on a spinning top, it makes it precess. I showed that to you. Okay, I spun the bicycle wheel, and instead of toppling over, the bicycle wheel precessed. Okay, so let me do that again. So here is a spinning top, and the torque is making it precess. All right, so the Earth is spinning. It's a spinning top. Okay? And it turns out that if the Earth's density was uniform and perfectly symmetrical, then there's nothing you could do about it. But it's not symmetrical. Okay? It's not symmetrical. And the gravity of the moon and the sun is trying to topple the Earth over. Okay. So here's the Earth spinning, and the gravity of the moon and the sun is trying to topple the Earth like that. And if a torque acts, you saw that what the effect of the torque is to make it precess. Well, how do we know the proof of this? Okay, so so let's do the following. So let's say I'm Earth. I'm of course spinning. This is the universe, and that's the sky. Okay, so as I turn this way, every object in the universe is turning that way. Okay, so as I rotate like that, every object is rotating in the opposite direction. There's a couple of objects that are not moving. That object is not moving, the North Star. Okay, so as the Earth goes around, it's pointing at the same location. But now, if the Earth's axis precessed, then the North Star will be changing over time. All right, so has that been happening? So the Iraqis were very good astronomers, and they kept very good records. Okay, so 5,000 years ago, that was the North Star. Today, that's the North Star, and you can see that the Earth's axis has been precessed. And the period of precession is 26,000 years. All right, so what that means is the following. Oops. Okay. There you go. So when the axis is most tilted towards the sun, this is somewhere in the northern hemisphere, okay? And the Earth's axis precesses once in 26,000 years. So if you come back 13,000 years from now, the axis will be pointing that way. And in June, what you'll have is winter in the northern hemisphere. Okay, so you want summer weather in December, then you either move to Florida or come back in 13,000 years. Okay. So the Earth's axis is tilted in June, you have summer, and in 13,000 years, the axis will be pointing the other way, and you'll have winter in June. Yeah. All right. Okay, just quick 2 seconds. Okay. So how does the sun produce energy? What it does is, so what it's doing is, it's taking 4 hydrogen atoms, okay? And again, the hydrogen atoms are, of course, positively charged particles. And, okay, what it's doing is it's fusing them and making a helium nucleus. Okay? And in the process, 2 of the protons get converted to neutrons and so on. And something called a positron is emitted. This is a positron, which is a positively charged particle. We won't go into the detail of that. 4 protons got converted to a helium nucleus. All right, first thing you have to do, protons are positive charges. Well, why are they combining? You bring them close together, they should fly apart. They'll repel each other and fly apart. Okay, so why are they combining? It turns out, so there are 4 forces: strong force, electromagnetic force, weak force, and gravity. Okay, gravity is the weakest force, and you don't talk about gravity unless you're talking about large objects. Okay, this force turns out to be 100 times stronger than the electromagnetic force, except that for this guy to act, you have to be within 10 to the minus 15 meters. Again, that's the size of a nucleus. So if you can bring 2 protons within 10 to the minus 15 meters, then the strong force will take over and you'll form a bound state. Now, to bring them that close, you have to move them very fast, and so you have to be in the center of the sun, very hot protons, and then they'll come together. All right, so these guys, you can arrange conditions so that they combine to form a helium nucleus. Well, what is the big deal? See, the mass of the 4 hydrogen atoms, 4 hydrogen nuclei, is that 6.69 times 10 to the minus 27 kgs. Look at the mass of the helium, 6.64. Okay, this mass this way is less. Well, what happened to the other mass? So remember, whenever you formed a bound state, your mass reduced. And what happened to that mass? That got converted to energy. That's how the sun produces energy. So it's using this equation, E equal to mc squared. Yeah. It turns out that 1 part in 140 of the original mass is converted to energy in every reaction. Okay. So the sun was born 5 billion years ago and it'll die in about 5 billion years ago. So over its span of 10 billion years, the sun will lose 1 to 2% of its mass. Okay? And it will get converted to energy. Okay? And so in that process, all these elements are made. Okay? And you can get energy up to iron. What this graph is telling you is, that's telling you the average mass of the nucleon, a neutron or a proton. So as you trap a nucleon in a more and more massive nucleus, its mass is getting less and less, and you're releasing energy. It's being bound stronger and stronger. All these guys, they're heavier. Fusion reaction can't make those guys. You need energy to make all those nuclei. By the way, so nuclear fission relies on the fact that uranium, the average mass per nucleon is higher, and you break this guy into smaller pieces, each of those guys weigh less, and that's released as energy. That's nuclear reactors. Okay. All right, so quickly, we'll talk about a supernova, and then we'll be done. Okay, so inside the sun, at the center of the sun, the temperature is 15 million degree Kelvin. So at 15 million degree Kelvin, you can fuse hydrogen to form helium. Then, if you want to make carbon out of helium, a helium nucleus is doubly charged, so you need to make it hotter to bring them close together. You need 100 million degree Kelvin. Okay. So eventually, when the sun runs out of hydrogen in its core and it doesn't have any more hydrogen to burn, it will collapse a little, the temperature will rise, and then helium, it'll start burning helium to carbon. To make carbon to other fusion reaction, you need to be even hotter. Eventually, you reach iron. Okay? So, and all this process will happen faster and faster toward the end. Because as the temperature rises, what happens? You're cooking faster. Okay? So all that will happen. Okay, so you're releasing energy till you get to iron. When you get to iron, what happens? Suddenly somebody turned off the gas. Okay? Okay, here was the sun. All this stuff wants to collapse. Okay? What is keeping the stuff from collapsing? All the heat is exerting a pressure that's keep holding that stuff up. As soon as you remove the source of heat, okay, what happens is the core collapses. Okay, so again, all this happens very, very fast. So once you reach iron in the core collapses, okay, and then all this falls down. Okay, so the core has collapsed, and now the outer stuff is falling down. This has become solid iron. It falls down, bounces off of this, and this bounced off stuff is colliding with this other stuff that's falling. Okay. In that collision, you have a lot of energy, And all that material, you're able to make a heavier element using that extra energy. Okay, and that thing will explode like a mother. Okay. So the core collapses in the span of about a second. The outer layers fall in and bounce off the collapsed core. This gravitational energy is used to produce heavier elements than iron. The bounce off the collapsed core produces a catastrophic explosion, a supernova. Yeah. And if the core collapse has a remaining mass greater than 1 point solar masses, the compressional force of the supernova explosion can be great enough to force protons and electrons together to make neutrons. So that core contains all neutrons, and that's a neutron star. Okay. So if the mass of the star of the collapsed core, if the mass is between 3 solar masses, this is the notation for solar mass, and 1.4 solar masses, this object is a neutron star. If you're greater than that, then you're a supernova. If you're less than that, then you're a white dwarf. All right, okay. Or a brown dwarf eventually. Okay, so here's a computer simulation. Here's the core collapsing, and you see it's collapsed within 3 milliseconds.